Tonight, we're going to look at the emptiest part of the solar system. Almost all of it. The familiar picture places 8 bright planets beside the sun like objects arranged on a shelf. A truthful picture would be mostly dark paper. The worlds would shrink toward invisibility, and the spaces between them would consume the page. But how empty is that darkness? Where does the solar system actually end? And why have the diagrams hidden its true shape so well? By the end of tonight, you're going to understand exactly how far apart the planets are, what occupies the apparent nothing between them, and why crossing the solar system means crossing several different kinds of boundary. Before we get started, if you love exploring the solar system as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The first distance to keep is 1 astronomical unit. 1 astronomical unit is 149,597,870.7 kilometers. It is approximately the distance from the Sun to Earth, fixed by astronomers as an exact unit, so that the enormous intervals of the solar system can be spoken without repeating long chains of digits. Light crosses 1 astronomical unit in about 8 minutes and 19 seconds. A radio command sent toward a spacecraft near Earth's orbital distance would already belong to a conversation delayed by minutes. That single unit contains almost no solid matter. At one end is the Sun, about 1.4 million kilometers across. At the other is Earth, only 12,756 kilometers across. Between their visible surfaces lie roughly 148 million kilometers of space. The objects are real. The interval is the dominant feature. Our journey will keep finding the same arrangement. A world. A long silence. Another world. The solar system is not a collection of neighboring spheres. It is a structure made primarily of separation. At true scale, you would spend most of the journey between visible destinations. Before moving outward, the name of the place needs a boundary. That is harder than it sounds. The solar system can mean the Sun and everything gravitationally bound to it. It can mean the region filled by the solar wind. It can mean the orderly neighborhood of the 8 planets. Each definition produces a different edge, and those edges are separated by distances larger than the planetary system itself. Neptune is the outermost planet, orbiting at an average distance of about 30 astronomical units. Yet calling Neptune the end would leave out Pluto, the Kuiper Belt, the scattered disk, and countless icy bodies whose paths are governed by the Sun. Far beyond Neptune, the solar wind inflates a vast bubble called the heliosphere. Voyager 1 and Voyager 2 have crossed the outer boundary of that bubble and entered interstellar space. They have not escaped the Sun's gravity. Farther still, models place the Oort Cloud, a spherical reservoir of distant comet nuclei. Its inner region may begin somewhere between 2,000 and 5,000 astronomical units. Its outer population may reach 100,000 astronomical units from the Sun. The nearest star is roughly 265,000 astronomical units away. By then, the word neighborhood has acquired a new scale. There is no painted wall. No sign announces that one system has ended and another has begun. The Sun's wind weakens until interstellar plasma dominates. The Sun's gravitational hold weakens until passing stars and the gravity of the galaxy become equally important. The neat circular map gives way to overlapping influences. For this reason, the journey will cross 3 endings: the last planet, the last reach of the solar wind, the last plausible orbits belonging to the Sun. Each ending is valid for a different question. None is nearby. From any one edge, you would find another solar influence continuing beyond it. The scale begins with a profound imbalance. The Sun contains about 99.8% of the solar system's mass. The 8 planets, their moons, dwarf planets, asteroids, comets, dust, and wandering fragments share almost everything left over. If the solar system were counted by mass alone, it would be reasonable to describe it as one star accompanied by residue. The Sun formed about 4.6 billion years ago as a cloud of gas and dust collapsed. Most material fell toward the center. Pressure and temperature rose until hydrogen fusion began. The remaining disk became the construction ground for planets and smaller bodies. That history left a system in which mass is concentrated at the center while orbital territory spreads far outward. The Sun's diameter is about 1.4 million kilometers. Earth's is about 12,756. Jupiter, the largest planet, is about 143,000 kilometers wide. More than 10 Jupiters could be placed across the Sun, and roughly 109 Earths could be span its diameter. Yet even this dominant star is small beside its own first major interval. From the Sun's center to Earth's orbit is more than 100 solar diameters. Volume makes the contrast stronger. Imagine a sphere reaching from the Sun to Neptune. The luminous Sun would occupy a minute fraction near the middle. The planets would contribute flecks. Almost every possible point inside that sphere would fall between solid bodies. Gravity does not require the intervening region to be filled. The Sun holds Earth from 149.6 million kilometers away without a rope or rigid track. Curved spacetime and motion sustain the orbit across the gap. The emptiness is not a failure of the system. It is the room in which the system works. The planets do not need to touch. They need only to keep falling around the same star. If you chose a random point inside Neptune's orbit, no solid surface would be near. Shrink the Sun to a sphere 14 centimeters across, about the size of a large grapefruit. On that scale, Earth is a grain only 1.3 millimeters wide. It cannot sit beside the grapefruit if distance is honest. It belongs about 15 meters away. A person standing near the model Sun would need to cross a large room before reaching a blue speck scarcely visible against a fingertip. Mercury would be 0.5 millimeter wide and about 5.8 meters from the Sun. Venus would be 1.2 millimeters wide at roughly 10.8 meters. Mars would be less than 0.7 of a millimeter at nearly 23 meters. 4 worlds fit inside the space of a modest building, but their sizes have become grains. Then the model leaves the building. Jupiter would be about 1.4 centimeters wide, placed almost 78 meters from the grapefruit Sun. Saturn would lie about 143 meters away. Uranus would require 287 meters. Neptune would be a blue-green bead nearly 450 meters from the center. The full planetary model needs a park, a long street, or several city blocks. This is why nearly every printed illustration cheats. If all 8 planets are large enough to recognize, the gaps will not fit. If the gaps are correct, the planets become points. An image can preserve the scale of the bodies or the scale of the distances, but on an ordinary page, it cannot comfortably preserve both. The compromise changes intuition. We remember colorful spheres and forget the dark intervals that actually define their arrangement. The true model restores the missing subject. A tiny object appears, followed by dozens or hundreds of meters, where almost nothing appears at all. One astronomical unit is 149,597,870.7 kilometers. In the grapefruit model, it becomes 15 quiet meters. The number has changed form. The emptiness has not. As you walk the model, the smaller worlds would vanish against ordinary ground. Mercury is the first planetary island, averaging 58 million kilometers from the Sun, or about 0.39 astronomical units. Sunlight reaches it in approximately 3.2 minutes. The planet itself is only 4,880 kilometers wide, a little larger than Earth's moon, and smaller than the largest moons of Jupiter and Saturn. Seen from Mercury, the Sun can appear more than 3 times wider than it does from Earth. At some points in Mercury's eccentric orbit, sunlight is about 7 times more intense than at Earth. Those facts make the planet sound close to the star. In human terms, it is not close at all. The gap between the Sun's surface and Mercury's average orbit is about 57 million kilometers. Earth could be laid across that distance thousands of times. Mercury completes an orbit in 88 Earth days, moving faster than any other planet. It does not race along a visible lane. There is no shining rail. The world crosses a region permeated by sunlight, solar wind particles, magnetic fields, and scattered dust, while almost never approaching a macroscopic object. The planet has no substantial atmosphere to distribute heat. Daytime temperatures near the equator can rise to about 430 degrees Celsius, while night temperatures can fall near minus 180. These extremes occur on one small surface, turning slowly within an enormous surrounding volume. A spacecraft sent there must aim not merely at a planet, but at a future point on a moving orbit. Mariner 10, Messenger, and Bepi Colombo used carefully shaped paths and planetary flybys because falling inward toward the Sun demands the removal of orbital energy. The empty region is easy to cross without collision and difficult to navigate with precision. Mercury is close to the Sun only by the standards of planets. By the standards of anything built on Earth, it is already across a gulf. Looking back from Mercury, you would usually find Earth as an unresolved point. The next planet is Venus, at an average distance of 108 million kilometers from the Sun. Subtract Mercury's average orbital distance, and the result is about 50 million kilometers. That arithmetic is useful, but it does not describe a permanent road between two worlds. The planets move at different speeds. Mercury completes more than 4 orbits during one Earth year. Venus takes about 225 Earth days to circle the Sun. Sometimes Mercury and Venus occupy the same general side of their orbits. At other times, the Sun stands between them. Their direct separation constantly changes. This moving geometry explains why mission planners speak of launch windows. A spacecraft cannot point toward the place where a planet is visible and continue straight ahead. It follows an orbit around the Sun, arranged so that the spacecraft and destination arrive at the same region at the same time. The transfer path is a meeting of 2 clocks. In a diagram, orbital rings seem to provide structure. In space, those rings are mathematical descriptions, not material bands. A spacecraft does not cross a painted circle when it passes Mercury's orbital distance. Instruments may detect gradual changes in plasma, dust, heat, and radiation, but the geometry itself remains invisible. The 50 million kilometer radial gap between Mercury and Venus therefore contains no fixed midway station. No planet guards the boundary. There are asteroids whose orbits enter the inner solar system, grains that scatter sunlight, and streams of charged particles flowing outward. Almost all the volume remains open. The first 2 planets are not adjacent beads. They are moving targets on separate tracks with an interval large enough to contain the Earth-Moon distance more than 100 times. Between their orbital paths, you would cross no physical seam or painted lane. Venus is about 12,104 kilometers wide, only slightly smaller than Earth. This resemblance is one reason it is often called Earth's sister planet. The phrase refers to bulk size and nearby orbit, not to a shared environment. Venus is wrapped in a dense carbon dioxide atmosphere and has a mean surface temperature around 464 degrees Celsius. It is the hottest planet, even though Mercury lies closer to the Sun. Its average solar distance is 0.72 astronomical units. Sunlight takes about 6 minutes to arrive. Earth follows at 1 astronomical unit, another 41.6 million kilometers farther from the Sun in radial terms. But Earth and Venus are not normally lined up with that minimum difference between their orbital sizes. At a favorable close approach, the planets can be roughly 38 million kilometers apart. When they occupy opposite sides of the Sun, their separation can exceed 250 million kilometers. The same pair of nearly equal spheres can be comparatively near or separated by more than the distance from the Sun to Mars. Radar, radio, and spacecraft navigation make those changing distances measurable. A signal cannot return instantly. At 38 million kilometers, one-way light time is a little over 2 minutes. Across 250 million kilometers, it approaches 14 minutes. Any machine operating at Venus must handle local conditions while Earth waits for old information to arrive. The darkness between the planets produces delay. It turns every interplanetary command into a message addressed to the future. Venus also shows why visual brightness says little about distance or size. It can become the brightest planet in Earth's sky because reflective clouds return sunlight efficiently and because its orbit brings it relatively near. A brilliant point overhead is still a whole world across tens of millions of kilometers. From Venus, you would need magnification to resolve Earth as more than light. Earth feels like the reference point because every measurement begins here. In the larger map, it is another small body moving through an immense interval. Its average orbital distance defines the ruler. 1 astronomical unit is 149,597,870.7 kilometers. Earth covers that orbit in about 365.25 days while rotating once in roughly 24 hours. The moon makes Earth appear less isolated. It orbits at an average distance of about 384,400 kilometers. That is slightly more than 30 Earth diameters, an enormous local interval by the scale of either world. Yet compared with 1 astronomical unit, the lunar distance is only about 1 part in 389. On a solar system map, Earth and Moon nearly occupy the same dot. In the night sky, they define a complete local system. Radio needs about 1.3 seconds to travel from Earth to the Moon. Apollo conversations included the resulting pause on a round trip. Minutes are not yet required. The Moon belongs to our immediate cosmic address. Beyond the Moon, Earth's influence does not end abruptly. Its magnetosphere forms a region shaped by the solar wind. Objects occupy stable and unstable orbital zones. The Sun and Earth create 5 Lagrange regions where their combined gravity and orbital motion allow spacecraft to maintain useful configurations. None of these places is a solid platform. They are patterns in motion. Earth's neighborhood contains satellites, discarded rocket stages, natural dust, and small near-Earth asteroids. It is crowded compared with the deep intervals between planets. Even here, occupancy is extremely sparse by terrestrial standards. Thousands of operational satellites can share near-Earth space because the available volume is large and carefully managed, though some orbital shells now require serious collision monitoring. From the surface, Earth seems to fill the world. From 1 astronomical unit away, it is a blue point. Scale changes the meaning of the home without changing its value. From lunar distance, you would already see Earth surrounded by far more darkness. The word empty needs restraint. Interplanetary space is not a perfect vacuum. The Sun continuously releases the solar wind, a flow of electrons, protons, and other charged particles. Near Earth, particle density is often only a few particles per cubic centimeter, changing with solar activity. That is extraordinarily thin beside air at sea level, where a cubic centimeter contains on the order of 10 billion molecules. Magnetic fields travel with the solar wind. The rotating sun draws the interplanetary magnetic field into a vast spiral pattern. Energetic particles pass through it. Solar eruptions can push denser, faster structures outward, disturbing planetary magnetospheres days after events on the sun. Dust is present as well. Grains released by comets and asteroid collisions orbit the sun. Sunlight scattered by this dust produces zodiacal light, a faint wedge sometimes visible before dawn or after evening twilight. Earth crosses streams of debris that become meteor showers when particles strike the atmosphere. The region also carries light in every direction. Direct sunlight dominates near the inner planets. Reflected light returns from worlds and dust. Infrared radiation leaves warmed surfaces. Radio signals from spacecraft cross the apparent void as encoded electromagnetic waves. None of this fills space in the way water fills a glass. The particles are widely separated. Fields do not provide a surface. Dust grains do not form a fog that a traveler would see rushing past. A spacecraft may travel millions of kilometers without encountering anything large enough to notice, while its instruments continuously measure plasma, radiation, and magnetic change. The best description is a very thin environment. It has weather without air, currents without rivers, and boundaries without walls. Matter is scarce. Influence is everywhere. A detector beside you would remain busy while the window looked nearly blank. Mars moves at an average distance of about 227.9 million kilometers from the Sun, or 1.52 astronomical units. Sunlight requires roughly 12.5 minutes to reach it. A noon sky on the surface receives less than half the solar energy that reaches the top of Earth's atmosphere, though the exact amount changes because the Martian orbit is more elliptical than Earth's. The planet is 6,792 kilometers wide, a little more than half Earth's diameter. Its land area is close to the total area of Earth's continents because oceans cover most of our own world. This smaller sphere carries the immense shield volcano Olympus Mons and Valles Marineris, a canyon system about 3,870 kilometers long. Mars is compact enough to fit inside Earth with room around it, yet its landscapes extend across continental scales. The local neighborhood includes Phobos and Deimos, two small dark moons discovered by Asaph Hall in 1877. Phobos circles only about 6,000 kilometers above the Martian surface and completes an orbit 3 times during a Martian day. Deimos travels farther out and takes about 30 hours. Even the close moon Phobos is separated from the ground by a gap comparable to a journey across a continent. Earth and Mars can approach within tens of millions of kilometers, but that is not their usual arrangement. At an unfavorable alignment, they stand on opposite sides of the Sun, separated by hundreds of millions. Radio delay between the planets varies accordingly, from a few minutes one way to more than 20 minutes. A rover cannot be driven with a live steering wheel from Earth. It receives plans, evaluates immediate hazards, and acts while its human team waits in the past. That delay is an operational form of emptiness. The space contains no obstacle large enough to block the signal, but it contains so much distance that even light cannot make the exchange immediate. Mars is the last terrestrial planet. Beyond its orbit, the architecture opens. On Mars, you would receive every ordinary message from Earth minutes after transmission. Jupiter's average orbit lies about 778.6 million kilometers from the Sun. Mars averages 227.9 million. The radial difference is approximately 550.7 million kilometers, more than the full distance from the Sun to Mars twice over. Expressed in the system's own ruler, the interval is about 3.68 astronomical units. One astronomical unit is 149,597,870.7 kilometers. The step from Mars to Jupiter is therefore not one familiar unit, but nearly four. Sunlight could cross the radial difference in about half an hour. A present-day spacecraft needs years, with its path and speed shaped by launch energy, planetary geometry, and sometimes gravity assists. The region is not entirely vacant. The main asteroid belt occupies part of it, broadly between the orbits of Mars and Jupiter. Several groups of smaller bodies share related orbital patterns. Comets pass through on stretched paths. Dust spreads across the plain. Still, the belt does not fill the gulf. It places isolated objects inside a volume so broad that an observer standing on most of those objects would see no other asteroid as a nearby looming rock. Temperature changed across the young solar nebula. Farther from the infant sun, more volatile materials could remain frozen and join growing bodies. The region around the present asteroid belt and beyond marked a transition in available building material. Jupiter accumulated an enormous atmosphere of hydrogen and helium. Mars remained a small rocky world. Between them, a planet never assembled. Jupiter's gravity helped prevent the belt's material from calmly merging into one large body. Repeated gravitational disturbances altered orbits and raised collision speeds. Some fragments struck planets, some left the system. Some survived for 4.6 billion years as a thin archive of planetary construction. The long interval between Mars and Jupiter therefore contains evidence, not congestion. Its scattered rocks record a failed assembly process. The space around those rocks records how little material remained. Midway through that crossing, you would have no large world as a landmark. Cinema often turns the asteroid belt into a moving wall. Boulders crowd every direction, and a spacecraft must twist between collisions. The real belt is almost the opposite. Asteroids are numerous when counted across the entire region, but their individual sizes are small, and their available volume is immense. NASA's Dawn team offered a useful order of magnitude model. If the belt contained 2 million asteroids at least 1 mile wide distributed through an estimated volume, the average separation between such bodies would be around 1.9 million miles, or about 3.1 million kilometers. That is roughly 8 times the average Earth-Moon distance. The estimate depends on assumptions about population and shape, but the conclusion is stable. Large asteroids do not brush shoulders. Spacecraft have crossed the belt many times. Pioneer 10 became the first to do so on its way to Jupiter in the early 1970s. Voyagers, Galileo, Cassini, Juno, and New Horizons followed on outward trajectories. Mission planners track known objects and evaluate small particle risks, but no pilot needs to dodge a continuous field of tumbling mountains. Collision is still part of the belt's history. Over millions and billions of years, orbiting bodies occasionally meet. Their impacts break families of fragments from parent asteroids and replenish interplanetary dust. Time permits rare events to accumulate. A region can be sparse at every moment and still be shaped by collisions over the age of the solar system. The combined mass of all known asteroids is less than the mass of Earth's moon. Most of that asteroid mass is concentrated in a few large bodies. Ceres alone accounts for a substantial fraction. Vesta, Pallas, and Hygiea add much of the remainder. The countless smaller objects contribute names and numbers far more rapidly than they contribute mass. The belt is best pictured as a vast annulus traced by lonely islands. Its title sounds solid. Its reality is orbital statistics spread through darkness. Inside the real belt, you would never see a continuous tunnel of rocks. Ceres is the largest body in the main belt and the only dwarf planet in the inner solar system. Its diameter is about 940 kilometers. That makes it wide enough to cross several states, but too small to look like more than a point across most of the belt. It travels at an average solar distance close to 2.8 astronomical units and takes about 4.6 Earth years to complete an orbit. Vesta is smaller, roughly 525 kilometers across, and bears the immense Silvia impact basin near its south pole. The basin is almost as wide as Vesta itself. Material blasted from ancient impacts eventually reached Earth as meteorites, allowing pieces of one specific asteroid to be studied in laboratories long before a spacecraft orbited it. Dawn entered orbit around Vesta in July 2011, remained for more than a year, then departed under ion propulsion. It reached Ceres in March 2015 and became the first spacecraft to orbit two extraterrestrial destinations. The journey from Vesta to Ceres took about 2.5 years, even though both bodies are usually drawn inside the same narrow belt. That travel time restores the missing scale. A map may place two labels near each other. The actual destinations continue moving around the sun while separated by changing distances. Dawn followed a gradual spiral of orbital energy rather than a straight hop from one rock to the next. Ceres contains bright salt deposits, including those in Okator crater, and evidence of water-rich chemistry. Vesta is differentiated with crust, mantle, and core, resembling a small protoplanet. They are not interchangeable rubble. Each followed a distinct geological path. The belt's two best explored worlds demonstrate that sparse does not mean monotonous. Diversity survives in isolated places. One rounded world, one battered protoplanet, millions of kilometers between them. The emptiness keeps their records separate. Near Ceres, you would not find Vesta looming anywhere in the surrounding sky. Jupiter averages 5.2 astronomical units from the Sun, about 778 million kilometers. Sunlight takes roughly 43 minutes to reach the cloud tops. A radio message from Earth can require more than half an hour one way when geometry is favorable and longer when the planets are more widely separated. The planet is about 143,000 kilometers wide at the equator, 11 times Earth's diameter. It is the largest planet and holds more mass than all the other planets combined. Yet Jupiter occupies almost none of the territory assigned to its orbit. In the 14-centimeter Sun model, Jupiter is a sphere only 1.4 centimeters wide, located roughly 78 meters from the center. One astronomical unit is 149,597,870.7 kilometers. Jupiter's orbital radius contains more than 5 of those units. The broad leap from the inner planets has made the Sun look smaller, but the star remains the controlling mass. Jupiter takes just under 12 Earth years to orbit it. Jupiter's strong gravity creates a large local domain. The planet gathers moons, shapes rings, traps charged particles, and shares its orbit with Trojan asteroid populations clustered around stable regions ahead of and behind it. These features give Jupiter the presence of a miniature system. They do not make the interplanetary approach crowded. NASA's Juno spacecraft launched in August 2011 and entered Jupiter orbit in July 2016 after traveling about 2.8 billion kilometers along a looping trajectory that included an Earth gravity assist. Its accumulated path was far longer than the straight-line distance between average orbits. Space navigation measures routes, not merely separations. From Juno's approach, Jupiter grew from a bright point into a banded disk. Until late in the crossing, the largest planet remained visually small. Size does not defeat distance quickly. The giant waits at the far end of its own darkness. Approaching Jupiter, you would watch the point become a world only gradually. Jupiter's 4 largest moons were seen by Galileo Galilei in January 1610. Io, Europa, Ganymede, and Callisto provided direct evidence that not everything circles Earth. They also reveal how a planetary neighborhood compresses distances that seem immense on a human map. Io averages about 422,000 kilometers from Jupiter's center. Europa lies near 671,000 kilometers, Ganymede about 1.07 million, and Callisto roughly 1.88 million. The full span from Jupiter to Callisto is larger than 4 Earth-Moon distances. Yet compared with Jupiter's 778 million kilometer distance from the Sun, the Galilean system is compact. Ganymede is 5,268 kilometers wide, larger than Mercury. It possesses its own intrinsic magnetic field. Europa is smaller than Earth's moon and hides a global ocean beneath an icy shell, according to multiple lines of evidence. Io is the most volcanically active body known, heated by repeated tidal flexing. Callisto preserves an ancient, heavily cratered surface. These are substantial worlds. A map of the solar system that gives them recognizable disks must enlarge them beyond scale. Otherwise, even Ganymede disappears. Around the true-size Jupiter model, the moons would be grains placed centimeters away, while the next major planet would stand tens of meters farther on. Jupiter also possesses many smaller moons, some following distant, tilted, or retrograde orbits. The exact count changes as discoveries are confirmed and classifications refined. Counting alone can make the region sound full. Volume supplies the correction. Even hundreds of moons share a domain millions of kilometers wide without forming a continuous swarm. Within Jupiter's magnetosphere, charged particles create an environment that is far from inert. Radiation can damage spacecraft electronics. Io supplies material through its volcanic gases, feeding a torus of plasma around the planet. Here again, empty space carries structure. The solid worlds are separated, while fields and particles connect them. Jupiter is an archipelago rather than a single island. The ocean around it remains dark. From Ganymede, you would still see the other major moons as separated worlds. Saturn averages 9.58 astronomical units from the Sun. Jupiter averages 5.20. The radial interval between their orbits is about 4.38 astronomical units, or roughly 655 million kilometers. The gap from one giant planet to the next is greater than the Sun-Jupiter distance, measured from Earth's orbit outward. Sunlight reaches Jupiter after about 43 minutes and Saturn after about 80. The added light time alone is around 37 minutes. A beam could cross the orbital difference in well under an hour. Voyager 1 needed about 20 months to travel from its Jupiter encounter in March 1979 to Saturn in November 1980, following a fast gravity-assisted trajectory. Cassini took a much longer route to reach Saturn, using flybys of Venus, Earth, and Jupiter after its 1997 launch before arriving in 2004. The contrast shows why there is no single travel time for a given distance. Spacecraft start with different launch vehicles, carry different masses, follow different mission designs, and must reach planets at usable angles and speeds. Arriving too fast can be as limiting as moving too slowly. An orbiter must shed enough relative energy to be captured. A flyby can preserve speed and continue outward. Between the two planets lie populations of small bodies, including centaurs whose unstable orbits cross the realm of the giant planets. Comets pass through. Dust and solar wind continue outward. None forms a visible chain between Jupiter and Saturn. For much of a spacecraft's cruise, daily operation is an exercise in patience and precision. Antennas remain pointed. Instruments are calibrated. Small course corrections accumulate. The target is still a point. The emptiness is not dramatic moment by moment. It is duration, 4 1/3 astronomical units, hundreds of millions of kilometers, months or years in transit. Then gradually, rings appear around a pale bead. On most cruise days, you would see no obvious change in the star field. Saturn is the sixth planet and the second largest. Its equatorial diameter is about 120,500 kilometers, roughly 9.5 Earth diameters. From an average distance of 1.4 billion kilometers, the planet receives sunlight after about 80 minutes. A Saturnian year lasts 29.4 Earth years. The planet rotates quickly, completing a day in about 10.7 hours. Rapid rotation contributes to its visibly flattened shape. Saturn's atmosphere is mostly hydrogen and helium, and the world has no solid surface where a spacecraft could stand. Pressure and temperature increase downward until the familiar distinction between gas and liquid loses simplicity. On a page, the rings make Saturn seem broad enough to command the outer solar system. In the scale model, the main planet is about 1.2 centimeters wide and weighs 143 meters from the grapefruit sun. The spectacular ring system adds only a few centimeters. The next planet remains another 144 meters away. Cassini entered orbit on July 1, 2004, after a journey of nearly 7 years. It then spent 13 years exploring Saturn, its rings, and its moons. The long residence changed a distant point into a dynamic place. Storms moved, seasons advanced, ring structures shifted, and moons exchanged material with their surroundings. Titan, Saturn's largest moon, has a dense nitrogen-rich atmosphere and stable lakes and seas of liquid methane and ethane at its surface. Enceladus sends jets of water, vapor, and ice grains from fractures near its south pole, feeding Saturn's broad E-ring. Small moons sculpt narrow ring edges through gravitational resonances. These connections create a rich local environment across millions of kilometers. Beyond it, the darkness resumes almost immediately. Saturn's neighborhood is active because matter and gravity are concentrated there. Its orbital territory is vast because nearly everything else is absent. The rings announce the island. The interval defines the map. Near Saturn, you would encounter a complete local system after years of transit. Saturn's main rings can extend about 282,000 kilometers from one side of the system to the other, nearly 3/4 of the average distance between Earth and the Moon. Their typical vertical thickness in the main rings is only about 10 meters. A structure wider than many worlds can be thinner than the length of a large room. That proportion is difficult to draw. A true scale edge-on illustration would make the rings vanish. Artists and diagrams thicken them so the structure remains visible. The adjustment is useful, but it can suggest a solid platter. The real rings consist of countless particles, mostly water ice, each following its own orbit around Saturn. Particles range from dust-sized grains to chunks as large as a house, with a smaller number of still larger pieces. Locally, the rings can be much more densely populated than interplanetary space. Collisions occur. Gravitational wakes form. Moonlets open gaps or maintain edges. Yet the rings contain open space even within their brightest bands. The Cassini division between the A and B rings is about 4,700 kilometers wide. It looks dark through a modest telescope, but it is not completely empty. Resonances with the moon mimas reduce particle density and organize orbits. Darkness in an image can indicate fewer particles rather than none. The ring plane teaches the central lesson in miniature. A bright structure may be mostly separation. A dark gap may still contain material. Scale and density change from place to place, and ordinary words lose precision. Seen from far away, billions of independent particles become one pale band. Seen from within, the band resolves into orbiting fragments with intervals between them. Seen edge-on, the whole architecture nearly disappears. The solar system behaves the same way at a larger scale. Planets become a row only when distance is compressed. Restore the distance, and the row dissolves into islands. Between ring particles, you would find open paths inside an apparently solid band. The journey from Saturn's orbit to Uranus changes the scale again. Saturn averages 9.58 astronomical units from the Sun. Uranus averages 19.20. The radial difference is about 9.62 astronomical units, approximately 1.44 billion kilometers. The empty step between these two neighboring planets is almost equal to Saturn's entire distance from the Sun. One astronomical unit is 149,597,870.7 kilometers. More than 9.5 such units fit between Saturn and Uranus. Sunlight needs about 80 minutes to reach Saturn, and about 2 hours 40 minutes to reach Uranus. The difference in light time is longer than many feature films, even though light makes the crossing at nearly 300,000 kilometers every second. In the grapefruit model, Saturn stands 143 meters from the Sun. Uranus stands 287 meters away. The gap is another 144 meters, virtually repeating the complete walk from the model Sun to Saturn. No planet occupies that long path. A few small body populations cross portions of it, and each remains an isolated traveler. Centaurs are icy bodies with orbits among the giant planets, often crossing or approaching the paths of one or more giants. Their configurations are unstable over long astronomical times because repeated gravitational encounters alter them. Some may be scattered inward and become short-period comets. Others may be thrown outward. They are temporary residents of a wide and changing district. Charon, discovered in 1977, travels mainly between Saturn and Uranus and shows comet-like activity despite its large distance from the Sun. Chariklo, discovered in 1997, has a narrow ring system of its own. These discoveries add structure to the gap without filling it. A ringed small body, hundreds of kilometers across, remains minute inside a region billions of kilometers wide. Only one spacecraft has crossed this interval and continued to Uranus. Voyager 2 passed Saturn in August 1981 and reached Uranus in January 1986. The transit lasted more than 4 years. During most of it, no world grew large in the camera. Navigation depended on radio tracking, star references, and careful predictions of motion. At Saturn's distance, a command and reply can require nearly 3 hours when Earth and Saturn are widely separated. At Uranus, round-trip communication can approach 6 hours depending on planetary positions. Engineers cannot wait for a real-time response to each action. Sequences are prepared, transmitted, and allowed to unfold far beyond immediate supervision. The solar wind continues through the gap, thinning as its particles spread across greater area. Sunlight weakens according to the square of distance. At Uranus, a given surface receives roughly 1/4 of the sunlight available at Saturn because the distance from the Sun has nearly doubled. Nothing sudden marks this decline. The star grows smaller. Power budgets become tighter. Radio signals become fainter. The same physical laws operate, but every exchange must cross more space. Saturn is not followed closely by Uranus. Saturn is followed by almost 10 astronomical units, and only then by another world. Halfway between them, you would be farther from either planet than intuition suggests. Uranus is about 51,118 kilometers wide, 4 times Earth's diameter. It is slightly wider than Neptune, but less massive. Methane in its atmosphere absorbs red wavelengths and helps produce the planet's muted blue-green color. Beneath the atmosphere lies a deep interior rich in water, methane, and ammonia under pressures and temperatures far removed from familiar ice. The planet's most recognizable property is its tilt. Uranus rotates with an axial tilt of about 97.8 degrees, so its spin axis lies nearly in the plane of its orbit. It appears to roll around the Sun. A major collision early in its history is one possible explanation, though the precise origin of the tilt remains a subject of research. One Uranian day lasts about 17 hours. One Uranian year lasts 84 Earth years. For nearly a quarter of that long orbit, one pole leans broadly toward the Sun, while the other faces away. The seasonal pattern unfolds across human lifetimes, and each season lasts about 21 Earth years. William Herschel identified Uranus as a new planet in 1781, the first planet discovered with a telescope. Its average distance is 2.9 billion kilometers. Sunlight arriving there began its journey about 2 hours and 40 minutes earlier. From Uranus, the Sun still outshines every other object, but its apparent disk is much smaller than from Earth. Voyager 2 made its closest approach on January 24, 1986, passing about 81,500 kilometers above the cloud tops. The encounter revealed additional moons, 2 previously unseen rings, an unusual magnetic field, and a rotation period close to 17 hours. It remains the only close spacecraft visit to Uranus. The brief flyby illustrates a severe economy of distance. 8.5 years passed between Voyager 2's launch in August 1977 and its Uranus encounter. The most detailed observations were concentrated around a narrow window of days. The spacecraft could not break into orbit with its available mission design. It gathered what it could and continued toward Neptune. Uranus has a system of faint rings and 28 known moons in current NASA summaries. Many inner moons are small, dark, and packed into orbital relationships close to the planet. The 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, are worlds of ice and rock with varied surfaces. Titania, the largest, is about 1,578 kilometers wide. Miranda, only about 472 kilometers across, carries cliffs, grooves, and a patchwork terrain that suggests a complicated geological past. These features occupy small solids embedded in a magnetosphere millions of kilometers long. The magnetic field is tilted nearly 60 degrees from the rotation axis and offset from the planet's center. As Uranus turns, its magnetosphere traces a twisted structure downstream. Empty-looking space becomes a changing field geometry that no ordinary camera can photograph directly. Uranus is quiet in visible light, distant in time, and rich in invisible motion. Its pale disk is the small marker for a large domain. Above Uranus, you would see faint rings circling a world turned sideways. Neptune averages 30.05 astronomical units from the Sun. The radial difference from Uranus is about 10.85 astronomical units, or more than 1.6 billion kilometers. That single interplanetary gap is greater than Saturn's entire average distance from the Sun. Place the grapefruit sun at one end of the scale model. Uranus is 287 meters away. Neptune waits at about 450 meters. The walk between those 2 blue planets is roughly 163 meters. It is longer than the scale model journey from the Sun past Saturn. At each end, the planet is a bead about 5 millimeters wide. Light needs roughly an hour and a half to cross the orbital difference. A radio conversation from Earth to a spacecraft near Neptune is delayed by about 4 hours in one direction, varying with geometry. A question sent in the morning may not produce a returned answer until late in the day. Voyager 2 crossed from Uranus to Neptune between January 1986 and August 1989. The spacecraft traveled for another 3 years and 7 months after its Uranus encounter. It was already beyond the reach of repair, carrying computers with capabilities tiny by modern consumer standards, powered by radioisotope generators whose electrical output slowly declined. The path was not an empty straight tunnel. Voyager moved along a solar orbit shaped by previous gravity assists. It sampled magnetic fields, charged particles, cosmic rays, and plasma waves. Its cameras could look back or ahead, but the destination remained small for most of the crossing. No large planet circles between Uranus and Neptune. Small bodies can enter the region on eccentric paths, yet repeated encounters with the giant planets make many such arrangements temporary. The outer planets have cleared broad zones near their own orbits over the age of the system. The phrase cleared an orbit does not mean every pebble has vanished. It means a planet has become gravitationally dominant in its orbital neighborhood, scattering, absorbing, trapping, or organizing much of the nearby material. Even a cleared zone can contain moons, rings, trojans, dust, and occasional crossing objects. Beyond Uranus, solar energy falls further. At Neptune's distance, sunlight is roughly 900 times weaker per unit area than at Earth because Neptune is about 30 times farther from the Sun. The inverse square relationship turns a factor of 30 in distance into a factor near 900 in illumination. Yet noon on Neptune would not be black. The distant sun would remain a concentrated, brilliant source. Human intuition often confuses a small apparent disk with a weak lamp. The sun at 30 astronomical units still provides enough visible light to illuminate clouds, rings, and icy moons. The region between the ice giants is therefore not beyond sunlight. It is a place where sunlight has become old by several hours and thinly spread across a sphere billions of kilometers wide. At the midpoint, you would still wait hours for any exchange with Earth. Neptune is the 8th and outermost planet, averaging about 4.5 billion kilometers from the Sun. Its equatorial diameter is approximately 49,528 kilometers, almost 4 times Earth's. It completes a rotation in about 16 hours and an orbit in about 165 Earth years. Since its discovery in 1846, Neptune has completed only one full revolution around the Sun. The planet was found through calculation before it was recognized through a telescope. Irregularities in the observed orbit of Uranus suggested the pull of another world. Urbain Le Verrier in France and John Couch Adams in Britain calculated possible locations independently. Johann Galle and Heinrich de Rest observed Neptune near Le Verrier's predicted position in September 1846. This discovery was gravity acting across emptiness. Uranus did not need a visible connection to Neptune. Small deviations accumulated in its motion, carrying information about an unseen mass more than 1 billion kilometers farther out. The gap itself became part of the measurement. Voyager 2 remains the only spacecraft to visit Neptune. It left Earth on August 20th, 1977, passed Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune on August 25th, 1989. The full planetary voyage to Neptune required 12 years. Its average velocity during that long crossing was about 19 kilometers per second. 19 kilometers each second is beyond ordinary experience. At that speed, a traveler could cross the continental United States in a few minutes. The spacecraft still needed 12 years because the route was measured in billions of kilometers and shaped by 4 moving planetary encounters. At Neptune, Voyager passed roughly 4,950 kilometers above the North Polar cloud tops. It detected a large storm, then called the Great Dark Spot, measured supersonic winds, studied the planet's magnetic field, discovered moons and rings, and continued toward a close pass of Triton about 5 hours later. Neptune's blue appearance comes mainly from methane absorbing red light, together with atmospheric processes that remain under study. Its atmosphere can drive winds faster than 2,000 kilometers per hour. Activity persists despite the planet receiving only a small fraction of Earth's sunlight. The planet has no solid surface in the familiar sense. Hydrogen, helium, and methane form the upper atmosphere. Deeper regions transition under pressure into dense fluids above a rocky core. The visible cloud top is a level in an atmosphere, not ground. Calling Neptune the last planet gives it the feeling of an edge. It is an edge only in classification. Beyond it lie a disk of icy worlds, a scattered population extending hundreds of astronomical units, the solar wind boundary, and the possible comet cloud surrounding everything. The last planet is not the last object. It is where the simple list of 8 ends. From Neptune, you would see the Sun as a brilliant but diminished point. Neptune's largest moon, Triton, is about 2,706 kilometers wide. It travels in a retrograde orbit, moving around Neptune in the direction opposite the planet's rotation. This reversed path strongly suggests that Triton formed elsewhere and was captured, probably from the population of icy bodies beyond Neptune. Capture on this scale would have rearranged Neptune's earlier moon system. Energy had to be removed from Triton's motion, perhaps through interactions with a former satellite or a binary companion. Whatever the exact sequence, the present regular moons close to Neptune and the irregular outer moons preserve traces of a disrupted past. Voyager 2 flew about 40,000 kilometers from Triton after its Neptune encounter. Images revealed a young-looking surface with few impact craters, broad plains, and dark streaks associated with active plumes. Nitrogen gas and dust rose several kilometers above the surface before winds carried material downrange. Activity existed at a solar distance of 30 astronomical units. Triton's surface temperature is near minus 235 degrees Celsius, among the coldest measured on a planetary body. Nitrogen, methane, and carbon monoxide can exist there as ices. A tenuous nitrogen atmosphere changes with the moon's long seasons. Neptune also has faint rings named Galli, Leverrier, Lassell, Arago, and Adams. The outer Adams ring contains concentrated arcs called Liberté, Égalité, Fraternité, and Courage. Ordinary orbital motion should spread particles more evenly, but gravitational interactions with the small moon Galatea help maintain the concentrations. The rings are narrow and dark. Their material does not form a solid hoop. Like Saturn's rings at much lower density and visibility, they are collections of orbiting particles organized by gravity. Voyager's geometry and image processing helped bring them out of the surrounding darkness. Neptune's moons occupy a broad range of distances. Tiny inner moons circle close to the rings. Nereid follows a highly eccentric orbit. Distant, irregular moons travel far out, likely captured objects. A list of names can sound crowded, while the orbits themselves extend across millions of kilometers. After Triton, Voyager 2 turned southward out of the plane in which most planets orbit. There was no next planetary target. The cameras would eventually be switched off. Fields and particles instruments continued to study the environment as the spacecraft moved toward the Heliopause. This departure changed the kind of exploration. Until Neptune, a large world provided a destination and a deadline. Beyond Neptune, the environment itself became the subject. Distance, plasma, dust, and the solar wind replaced a planetary disk. Neptune's neighborhood is the final archipelago arranged around a major planet. Past it, the islands become smaller, colder, and much farther apart. Standing in imagination on Triton, you would watch Neptune dominate an otherwise sparse sky. The main Kuiper Belt begins near Neptune's orbit at about 30 astronomical units and extends to roughly 50. Its shape is a thickened disk or broad donut aligned approximately with the planetary plane. The name belt again suggests a continuous band. In reality, it is a large region containing separated icy bodies on individual orbits. Its radial width is around 20 astronomical units. One astronomical unit is 149,597,870.7 kilometers. The main belt, therefore, spans about 3 billion kilometers from its inner to outer regions, before accounting for its thickness above and below the central plane. Entire planetary systems of the inner kind could fit inside that width. Observers have cataloged more than 2,000 trans-Neptunian objects, but surveys sample only part of the sky to limited brightness. Models suggest hundreds of thousands of bodies larger than 100 kilometers may inhabit the region. An estimated trillion or more comet-sized bodies may exist there. Those large totals are distributed through a volume that defeats ordinary intuition. The combined mass is small. NASA summaries estimate that all material in the Kuiper Belt may amount to no more than about 10% of Earth's mass. The early belt likely held much more. Interactions with the migrating giant planets scattered material inward, outward, and out of the solar system. Neptune shapes the surviving architecture through orbital resonance. Pluto belongs to a population called Plutonos, which complete 2 orbits for every 3 completed by Neptune. This stable rhythm prevents close encounters, even though Pluto's orbit can carry it closer to the Sun than Neptune. Other objects occupy the classical belt, including a dynamically colder population with less tilted, less eccentric orbits. The word cold here refers to orbital motion, not simply temperature. These bodies move in comparatively orderly paths and may preserve a less disturbed sample of early outer solar system material. Haumea spins rapidly and has an elongated shape. Makemake is a methane-rich dwarf planet. Quaoar, Orcus, Gonggong, and many smaller bodies expand the inventory beyond the best-known names. Their diversity emerged far from the Sun under cold conditions, but they are not pieces of one uniform shell. At 40 astronomical units, sunlight takes more than 5.5 hours to arrive. It is about 1,600 times weaker per unit area than at Earth. Surface temperatures allow volatile compounds to freeze, though sunlight and cosmic radiation continue to alter the uppermost material. A spacecraft crossing the Kuiper Belt is not surrounded by visible snowballs. New Horizons had to be aimed with extraordinary care at Pluto and later Eurokoth. The chance of casually passing close to a substantial body is extremely low because the region is so sparse. The belt is populous in a catalog and empty through a window. Both statements are true. Crossing it, you might travel years without passing near a substantial body. Pluto follows an eccentric orbit ranging from about 30 to 49 astronomical units from the Sun, and takes roughly 248 Earth years to complete one circuit. Its average distance is near 39.5 astronomical units. The world is about 2,377 kilometers wide, smaller than Earth's moon, and only about 2/3 the diameter of our moon. Charon, the largest of Pluto's 5 known moons, is roughly half Pluto's diameter. The two bodies are separated by about 19,600 kilometers from center to center and orbit a shared center of mass located outside Pluto. They present the same faces to each other, completing their mutual turn in about 6.4 Earth days. This close pair still occupies almost no part of Pluto's solar orbit. Their separation is less than the width of Earth, measured twice. The distance from Pluto to the Sun is measured in billions of kilometers. A binary-like local dance moves through a path so large that its own scale becomes invisible. New Horizons launched on January 19, 2006. It passed Jupiter for a gravity assist in February 2007 and reached Pluto on July 14, 2015, more than 9 years after leaving Earth. At closest approach, it flew about 12,500 kilometers above Pluto, moving too fast to enter orbit. The spacecraft returned evidence of a geologically active world. Sputnik Planitia, a bright basin dominated by nitrogen ice, shows cellular patterns consistent with convection. Mountains made largely of water ice rise along its margins. A layered atmosphere extends far above the surface and forms blue haze when seen in backlight. Charon revealed deep canyons and a dark reddish polar region. Smaller moons, Styx, Nix, Kerberos, and Hydra, circle farther out. The brief encounter replaced a handful of blurred pixels with complex landscapes, but the data did not arrive at once. One-way radio time near Pluto was about 4.5 hours. New Horizons stored observations during the encounter because Earth could not direct the rapid sequence in real time. Its transmitter then sent information across the solar system at a low data rate. The complete primary dataset required more than a year to return. Distance affected knowledge twice. It delayed the spacecraft's arrival by nearly a decade and delayed the arrival of each bit of information by hours. The empty crossing became part of the scientific instrument, limiting power, bandwidth, command, and memory. Pluto was reclassified as a dwarf planet in 2006 because it had not cleared its orbital neighborhood, not because the world had ceased to exist or lost geological interest. The category describes orbital context. New Horizons demonstrated the difference between classification and character. At the edge of the familiar chart, a small world turned out to have glaciers, mountains, haze, weather, and 5 moons. The surrounding darkness had hidden detail, not absence. From Pluto, you would wait hours for Earth's reply to begin its return. After Pluto, New Horizons continued deeper into the Kuiper Belt. On January 1, 2019, it flew past Rokoth, then designated 2014 MU69, at a solar distance of more than 43 astronomical units. Rokoth is a contact binary roughly 35 kilometers long, composed of 2 flattened lobes joined gently together. Its shape suggests that small building blocks in the early solar system could merge at low speed rather than through a violent collision. The surface is very red and only lightly cratered in the images returned. A body far smaller than Pluto preserved clues about the earliest stages of planet formation. Finding a reachable target was itself a problem of emptiness. The Hubble Space Telescope surveyed a narrow region ahead of New Horizons to identify objects close enough to the spacecraft's remaining path and fuel capacity. Rokoth was not a convenient stop along a crowded road. It was one small target selected from a sparse field under strict geometric limits. The main Kuiper Belt does not contain every distant body. Beyond and overlapping its outer edge lies the scattered disk, a population on elongated and tilted orbits, extending toward nearly 1,000 astronomical units. Neptune's past gravitational encounters helped create many of these paths. Eris travels between roughly 38 and 98 astronomical units and takes about 560 years to orbit. Sedna follows a still more detached path, never approaching the Sun closer than roughly 76 astronomical units and traveling outward toward about 1,000. Its orbit takes around 10,500 years. Objects such as Sedna are difficult to explain through Neptune alone because they remain too far away for ordinary close encounters. Proposed influences include early stellar passages when the Sun formed in a cluster, unseen distant populations, or other episodes in the solar system's youth. The evidence is incomplete, so their exact history remains open. This region dissolves the neat disk. Planetary orbits cluster near a common plane. Classical Kuiper Belt objects form a thickened extension. Scattered and detached objects reach far above, below, and outward on long ellipses. The architecture becomes less like a set of rings and more like overlapping threads. Orbital period becomes a kind of clock. Neptune takes 165 years. Pluto takes 248. Eris takes about 560. Sedna takes roughly 10.5 millennia. A single Sedna year is longer than all recorded human history. These worlds spend most of their time far from the Sun, moving slowly near the outer ends of their orbits. Discovery favors the shorter interval when they return closer and brighten. The catalog is shaped by where objects happen to be during the brief era of telescopic astronomy. Beyond 50 astronomical units, the solar system does not stop. It becomes harder to inventory. The spaces widen faster than the list grows. Beside Autokoth, you would find no second large object sharing the view. The planets and icy bodies orbit because of gravity. A different structure is created by the solar wind. The Sun's hot outer atmosphere releases a continual flow of charged particles, carrying solar magnetic fields outward. This expanding plasma inflates the heliosphere inside the surrounding interstellar medium. Near Earth, typical solar wind speeds are hundreds of kilometers per second, though conditions vary. Fast streams emerge from coronal holes. Coronal mass ejections can carry denser magnetic structures outward. By the time such disturbances reach Earth, they may trigger auroras and interfere with satellites, radio, and power systems. The Sun rotates while releasing the wind. Motion draws the embedded magnetic field into a spiral, often compared with water from a rotating sprinkler. The field's polarity and shape change with solar activity. Every planet moves inside this large magnetic environment, though each planet responds according to its own atmosphere and magnetic field. Earth's global magnetic field diverts much of the solar wind around a magnetosphere. Venus lacks a comparable intrinsic field, but develops an induced magnetic interaction. Mars carries remnant crustal fields. Jupiter's powerful magnetosphere creates a vast local cavity. The same sparse wind meets different islands and produces different boundaries. As the solar wind expands, its density and pressure decline. Far beyond the planets, it can no longer push outward freely against interstellar plasma. The flow slows through the termination shock and enters the heliosheath, a disturbed outer region. Farther out lies the Heliopause, where solar and interstellar influences meet. The distances are not identical in every direction. Voyager 1 crossed the termination shock at about 94 astronomical units in 2004. Voyager 2 crossed at about 84 astronomical units in 2007. Changing solar conditions and the asymmetric interaction with the interstellar medium help produce different boundary locations. The heliosphere is sometimes drawn like a comet with a long, narrow tail. Modern measurements and models suggest a more complicated form influenced by magnetic fields, solar cycles, and particle populations. Its exact global shape remains an active research question because only two spacecraft have directly sampled the heliopause. Neutral atoms from interstellar space can enter the heliosphere because they do not respond to magnetic fields in the same way as charged particles. Some become ionized and are picked up by the solar wind. Energetic neutral atoms created through particle exchanges allow missions such as IBX to map the boundary remotely. The bubble is not an airtight shell. Particles and radiation cross it. Galactic cosmic rays enter from outside, with their intensity modulated by solar activity. Solar particles travel outward. The boundary separates dominant plasma environments without isolating them completely. At Neptune, 30 astronomical units from the Sun, the planetary list ends. The heliosphere continues several times farther. The first large edge beyond the planets is not made of rock. It is made of pressure, motion, and magnetic fields in matter too thin to see. Inside that bubble, you would cross changing plasma without seeing a wall. The solar wind leaves the Sun at supersonic speed relative to the characteristic waves in its own plasma. For billions of kilometers, it expands outward with little resistance. Eventually, the pressure of the surrounding interstellar medium becomes important. The outward flow slows abruptly at a boundary called the termination shock. This is not the end of the solar wind. It is a change in its motion. Downstream of the shock, particles move more slowly, heat, and become turbulent within the heliosheath. The region resembles no simple atmospheric shell. It changes with the solar cycle and differs across direction. Voyager 1 crossed the termination shock in December 2004 at about 94 astronomical units from the Sun. Voyager 2 crossed in August 2007 at about 84 astronomical units. 10 astronomical units separated the two crossing distances, a difference roughly equal to the full span from the Sun to Saturn. The spacecraft did not reach the same part of a rigid sphere. Voyager 1 traveled north of the planetary plane while Voyager 2 traveled south. Solar activity changed between the encounters. The external magnetic field and interstellar flow distort the heliosphere. A living boundary moved around two machines taking different paths. One astronomical unit is 149,597,870.7 kilometers. At 84 astronomical units, sunlight takes nearly 12 hours to arrive. At 94 astronomical units, it takes about 13. A command transmitted from Earth requires roughly half a day to reach a spacecraft near those distances, then another half day or more for a reply. Voyager's instruments identified the transition through particles and fields rather than an image. Charged particle populations changed. Plasma behavior changed. The spacecraft continued through darkness that looked much the same to a camera, while its detectors recorded a new physical region. The termination shock offers a useful correction to ordinary boundary language. Crossing a border does not require seeing a surface. A thermometer can reveal the entry into warmer water. A particle detector can reveal the entry into a different plasma regime. The event is real even when the view remains black. Beyond the shock, the Sun is still plainly present. Its particles have merely slowed. The heliosheath still belongs to the bubble formed by solar activity. Voyager 1 crossed this region for nearly 8 years before reaching the heliopause. Voyager 2 spent more than 11 years there. The outer solar wind has thickness measured in billions of kilometers. Even the boundary layer is a journey. At the termination shock, you would notice instruments change before the view did. The heliopause marks the outer limit of the heliosphere in the direction sampled by each Voyager. Here, the outward pressure associated with solar plasma balances the surrounding interstellar environment. Solar wind particles become rare beyond it, while particles of galactic origin become more prominent. Voyager 1 crossed the heliopause on August 25, 2012, at about 121 astronomical units from the Sun. The crossing was not announced immediately by a visible flash or a single perfect reading. Scientists compared particle counts, magnetic measurements, and plasma wave observations to establish that the spacecraft had entered interstellar space. Voyager 1's plasma instrument had stopped working in 1980. Nature supplied an indirect measurement. Solar eruptions sent disturbances outward, causing the plasma around the distant spacecraft to oscillate. The plasma wave instrument detected the resulting tones. From their frequency, researchers inferred that the surrounding plasma was far denser than expected inside the heliosphere and consistent with interstellar space. Voyager 2 crossed the Heliopause in November 2018 at about 119 astronomical units. Its working plasma instrument directly observed a sharp decline in the outward solar wind flow. Other instruments recorded changes in particles and fields. Two passages, 6 years apart, confirmed that a solar boundary could be measured from more than one direction. The heliopause does not exclude every solar influence. Sunlight continues outward indefinitely, thinning with distance. The sun's gravity continues to govern objects far beyond. Solar eruptions can send waves through the heliosheath, and their effects help probe the boundary. The label separates plasma domains, not all possible meanings of solar system. The region outside is called the local interstellar medium. It contains matter between stars, thin plasma, neutral atoms, dust, magnetic fields, and cosmic rays. Voyager entered this medium while remaining much closer to the sun than to any other star. At approximately 120 astronomical units, the heliopause is 4 times farther from the sun than Neptune. In the grapefruit scale model, Neptune waits 450 meters away. The heliopause would be around 1.8 kilometers from the model sun, beyond the comfortable limits of a park and into the surrounding town. Crossing that line took Voyager 135 years after launch and Voyager 241. Both machines were designed in the 1970s for planetary encounters. Their extended mission transformed them into the first direct samplers of interstellar space. The second ending has been crossed. The solar wind is behind them. The solar system is not. Beyond the heliopause, you would still feel the sun defining the local trajectory. The phrase interstellar space sounds as though the spacecraft has left home completely. In plasma terms, it has. In gravitational terms, it has barely begun the outward journey. A body can move through interstellar plasma while remaining on a path overwhelmingly shaped by the sun. Gravity has no sharp cutoff. Its strength declines with the square of distance, but it never becomes exactly zero. At any location, multiple masses contribute. Near Earth, Earth and the Sun dominate different aspects of motion. Far outside the heliosphere, the Sun continues to dominate many comet orbits, while passing stars and the Milky Way add small, accumulating perturbations. Voyager 1 and Voyager 2 are not in closed orbits that will return them to the Sun. Their speeds exceed local solar escape speed, so absent an unlikely future encounter, they will continue into the galaxy. Escape trajectory is not the same as completed escape. They remain near the beginning of a voyage measured in tens of thousands of years. At 120 astronomical units, Neptune's orbit would fit between the spacecraft and the Sun 4 times. That sounds large until the modeled inner edge of the Oort Cloud appears around 2,000 to 5,000 astronomical units. The Voyagers have crossed the solar windshore and entered an ocean still surrounded by possible solar comets. The distinction matters whenever a headline says a spacecraft has left the solar system. The statement can be correct if solar system means heliosphere. It can be misleading if solar system means the complete gravitational family of the Sun. Precise language keeps both achievements and remaining distances in view. Sunlight at Voyager's distance is faint but not absent. At 120 astronomical units, the same area receives roughly 1/14,000th of the solar energy it would receive at Earth. The Sun would look like an intensely bright star rather than a disk with easily perceived width. The spacecraft do not rely on that weak light for electrical power. Their radioisotope thermoelectric generators convert heat from radioactive decay into electricity. Available power diminishes over time, so mission teams have gradually switched off heaters and instruments to preserve essential functions. Communication uses the Deep Space Network's large antennas. A transmitter with modest power sends a signal across more than 100 astronomical units. By arrival, the signal is extraordinarily weak. Careful receivers extract information from it, turning a few surviving watts and precise engineering into contact across interstellar plasma. Outside the bubble, there is still a line home. Not a physical cable, a narrow radio beam, a predicted position, and hours of light time. Beside Voyager, you would receive Earth's newest command as yesterday's message. The inner Oort cloud is thought to begin somewhere between 2,000 and 5,000 astronomical units from the Sun. The uncertainty is not a minor rounding difference. Its nearer estimate and farther estimate are separated by 3,000 astronomical units, 100 times Neptune's distance from the Sun. One astronomical unit is 149,597,870.7 kilometers. The gap from a 120 to AU Heliopause to a possible 2000 AU Oort boundary is about 1,880 astronomical units, or roughly 281 billion kilometers. It contains no known planet and no confirmed wall of comets. It is primarily a transition between better mapped inner populations and a modeled distant reservoir. On the 14-centimeter sun scale, Earth is 15 meters away, Neptune 450 meters, and the Heliopause about 1.8 kilometers. The nearer estimate for the Oort cloud begins around 30 kilometers from the model sun. The farther inner estimate begins around 75 kilometers away. The scale model has left the city. Voyager 1 travels roughly 3.6 astronomical units farther from the sun each year. NASA estimates that it may take about 300 years to enter the Oort cloud. That date would fall as far in our future as the early 18th century lies in our past. The crossing cannot be planned as a close flyby. Oort cloud bodies are expected to be separated by enormous intervals. Their sizes are small, their reflected sunlight extremely faint, and their precise positions mostly unknown. A spacecraft could pass through a populated theoretical cloud without ever photographing one nucleus at useful range. This is the opposite of entering a cloud on Earth. There may be no visible haze, no rising count of nearby specks, and no obvious moment of arrival. The cloud is defined statistically by a family of distant orbits, not by particles suspended close together. The region between the Heliopause and Oort cloud is sometimes treated as a blank margin on diagrams. Physically, it still contains interstellar plasma, cosmic rays, neutral atoms, dust, sunlight, and the sun's gravitational field. Small bodies on scattered or detached orbits may cross parts of it. Most have not been found. Detection becomes difficult because reflected sunlight weakens twice. Light spreads while traveling from the sun to an object. Then the reflection spreads again on its return to a telescope. A body twice as far away can become far more than twice as difficult to see, depending on size, surface, and geometry. Time deepens the obscurity. An object taking thousands or millions of years to orbit moves only a short arc during the era of modern observation. Astronomers infer the larger path from a small measured segment, with uncertainty growing toward the unseen reaches. The road to the Oort cloud is not empty of physics. It is empty of convenient landmarks. At 2,000 astronomical units, you would wait weeks for a round-trip signal. The planets in main Kuiper Belt preserve the flattened shape of the disk from which the solar system formed. The Oort cloud is expected to be different, a vast, roughly spherical distribution surrounding the Sun. Its objects may approach from any direction rather than remaining near the familiar planetary plane. This shape records gravitational scattering. Early in solar system history, the giant planets interacted with enormous numbers of icy planetesimals. Some were ejected completely. Others were thrown onto very long orbits. Passing stars in the overall tidal influence of the Milky Way could lift and rearrange those orbits, helping form a distant spherical reservoir. No spacecraft has observed the Oort cloud directly. No telescope has imaged it as a surrounding shell. Its existence is inferred mainly from the orbits of long-period comets that enter the planetary region from many directions. The model explains a pattern. It should not be mistaken for a photographed object. The inner edge may lie between 2,000 and 5,000 astronomical units. The outer edge may lie somewhere between 10,000 and 100,000. The broad ranges reflect both limited evidence and the fact that a gravitational population need not end at one precise radius. At 100,000 AU, sunlight takes about 1.58 years to arrive. The distance is roughly 15 trillion kilometers. On the grapefruit model, that outer estimate lies about 1,500 kilometers from the tiny sun. A model begun in one city would end in another country. Comet nuclei in this region may remain frozen and dark for most of their existence. A passing star or the galaxy's tidal field can alter an orbit slightly. Over a tremendous distance, a small change may send a nucleus inward. It can then spend millions of years falling toward the planetary system. As a comet approaches the sun, heat releases gas and dust, forming a coma and tails that can span millions of kilometers. A once invisible nucleus becomes one of the broadest visible structures in the night sky. The display is temporary. The source spent almost all its orbit in darkness. Long-period comets can require thousands or millions of years to return. Some will never return because planetary encounters or solar heating change their paths. Others may be first-time visitors from the outer reservoir. Reconstructing their origins requires separating gravitational history from non-gravitational effects caused by jets of escaping gas. The Oort cloud is therefore both part of the solar system and a margin continually influenced by the galaxy. The sun gathers the objects. The wider stellar environment can disturb them. Ownership becomes less exclusive with distance. It is the third edge, but it is an edge drawn in probability. Within that cloud, you might never see another nucleus without a telescope. Proxima Centauri, the nearest known star to the sun, is about 4.2 light-years away. 1 light-year is roughly 63,000 astronomical units, making the distance to Proxima close to 265,000 astronomical units. The outer estimate of the Oort cloud, 100,000 astronomical units, reaches a substantial fraction of the way, but remains far short of the star. At this scale, the sun is no longer best pictured as a center surrounded by empty infinity. It is one star among neighboring stars moving through the Milky Way. Each star may carry planets, debris, plasma structures, and perhaps its own distant cloud of comets. Their domains can be large without their bright surfaces being close. In the grapefruit model, the sun is 14 centimeters wide. Proxima would be a much smaller sphere, about 4,000 kilometers away. Earth would remain a 1.3 millimeter grain, only 15 meters from the model sun. The solar system's familiar worlds occupy the first few hundred meters of a model whose next star lies across a continent. Voyager 1 is not traveling toward Proxima Centauri. Its trajectory will carry it through the galaxy on a different path. In about 40,000 years, it will pass within roughly 1.6 light years of the star, Gliese 445, which itself is moving toward our region. Even that encounter will not be a visit in planetary terms. At Voyager's current kind of speed, crossing 4 light years would require tens of thousands of years. No working spacecraft has been designed to remain operational for such a span. The machines will become silent artifacts long before any moderately close stellar passage. The nearest star comparison also reveals why the Oort Cloud can be both enormous and sparse. A shell extending tens of thousands of AU has room for many comet nuclei, while leaving colossal separations between them. Large population and low density are not opposites when volume becomes astronomical. Passing stars need not enter the dense inner system to matter. A star traveling within a fraction of a light year can gently alter the outermost comet orbits. The effect on Earth would be negligible directly, yet accumulated changes far away may redirect comets over long periods. The Sun and Proxima are themselves orbiting the center of the Milky Way. The solar system completes a galactic circuit in roughly 230 million years. During that orbit, the stellar neighborhood changes. Stars approach and recede. The outer boundary is continually redrawn by motion. There is no permanent line halfway between suns. There is a shifting gravitational landscape in which one star dominates here, another dominates there, and the galaxy contributes everywhere. Beyond the last plausible solar comets, emptiness becomes interstellar not only in plasma, but in allegiance. Between the stars, you would measure belonging through motion rather than boundaries. Every useful solar system map chooses what to distort. A portrait preserves planetary appearance, but compresses distance. An orbital diagram preserves relative paths, but enlarges the planets. A logarithmic map compresses the outer reaches so that Earth, Neptune, the Heliopause, and Oort Cloud can share one page. These choices are not errors when they are labeled. The problem begins when the compromise is forgotten. A row of planets becomes an unconscious model of closeness. The asteroid belt becomes a wall. Neptune becomes the edge. Voyager appears just beyond the planets instead of decades beyond the launch. One page cannot easily show a 1.4 million kilometer sun, a 4,880 kilometer Mercury, their 58 million kilometer separation, and an Oort cloud reaching perhaps 15 trillion kilometers. The largest distance exceeds the smallest planetary diameter by billions of times. Ink and pixels need assistance from scale changes. Time offers a second map. Light reaches the moon from Earth in about 1.3 seconds. It reaches us from the sun in 8 minutes 19 seconds. From the sun, it needs about 43 minutes to Jupiter, 80 minutes to Saturn, 2 hours 40 minutes to Uranus, and a little over 4 hours to Neptune. A spacecraft offers a slower map. Apollo astronauts reach the moon in days. Typical Mars missions travel for months. Juno needed nearly 5 years to enter Jupiter orbit. Cassini needed almost 7 to reach Saturn. Voyager 2 needed 12 years to encounter Neptune and 41 to cross the Heliopause. The Oort cloud breaks even that ruler. Voyager 1 may require about 3 centuries to enter it, and perhaps 30,000 years to pass beyond its distant outer estimate. A mission that began within living memory becomes a journey longer than civilization's written record. Distance scale, light time, and spacecraft time describe the same architecture from different directions. Kilometers provide exact length. Light time explains communication. Mission time introduces energy and trajectory. No single number supplies the complete feeling. A truthful mental map therefore changes resolution. It can look closely at a moon system, then step outward to an orbit, then outward again to a plasma bubble, then outward again to a probabilistic comet shell. At every step, solid objects shrink and intervals grow. The missing feature in most illustrations is not another planet. It is the amount of paper that would have to remain blank. On a truthful page, you would recognize the solar system mainly by its spacing. Light time turns the invisible gaps into something operational. At Mercury's average distance, sunlight is about 3.2 minutes old. At Venus, it is roughly 6 minutes old. At Earth, it is 8 minutes 19 seconds old. At Mars, it is almost 13 minutes old. Each world sees a different historical sun. Farther out, the units change. Sunlight at Jupiter began its crossing around 43 minutes earlier. At Saturn, it is about 80 minutes old. At Uranus, 2 hours 40 minutes. At Neptune, a little over 4 hours. Near Pluto's average distance, sunlight has traveled approximately 5.5 hours. These are one-way times from the sun. Communication from Earth changes as both Earth and the destination move. A spacecraft near Mars may be only a few light minutes away during one part of the orbital cycle and more than 20 light minutes away during another. The direct geometric separation sets the delay. If you stood beside a control room engineer during a distant encounter, the screens would show an event that had already happened. A successful engine burn near Saturn might be more than an hour old when its first confirmation reached Earth. Any corrective command would arrive another hour or more later. The present exists locally, not across the whole solar system at once. Mission design therefore moves judgment outward. Landers detect hazards during descent. Rovers stop before obstacles. Spacecraft enter protective modes when readings move beyond safe limits. Human teams define goals and contingencies, but a machine far from Earth must carry enough rules to survive, while no reply can reach it. Data return also exposes distance. Radio energy spreads as it travels. A receiver intercepts only a minute fraction of the transmitted signal. Large antennas, low noise electronics, precise timing, error-correcting codes, and long integration recover information that would otherwise disappear beneath background noise. The Deep Space Network uses complexes in California, Spain, and Australia, spaced around Earth so rotation does not permanently turn the planet away from a mission. As one site loses a spacecraft below its horizon, another can take over. Earth itself becomes part of the moving communication geometry. At the Heliopause, one-way light time is around 17 hours. A command sent on one day may not reach a Voyager until the next. Confirmation can return another day later. Engineers must keep a mental model of a spacecraft whose true condition is always hours ahead of the latest received data. The distance to the inner Oort cloud would push delay from hours into days. At 2000 AU, light needs about 11.5 days to travel one way. At 100,000 astronomical units, a one-way message needs about 1.58 years. Conversation becomes correspondence across seasons. One astronomical unit is 149,597,870.7 kilometers. It is also 8 minutes 19 seconds of sunlight. The same unit can be held as length or weighting. Kilometers draw the map. Delay makes the map felt. In a deep space control room, you would work with a permanently delayed present. The solar system began with more material spread through a disk. Gas, dust, ice, and growing planetesimals collided and exchanged momentum. Gravity gathered some material into larger bodies. The young sun drew in most of the mass. Planet formation was a process of concentration. Concentration naturally creates empty regions. When grains join a planetesimal, the same mass occupies one compact object instead of a cloud of separate pieces. When a planet accretes, ejects or traps nearby bodies, its orbital neighborhood becomes less populated. After billions of years, the survivors trace stable arrangements rather than the original dense disk. The Sun holds about 99.8% of the total mass. Jupiter holds most of the planetary remainder. This leaves relatively little mass to distribute through the enormous volume reaching Neptune and beyond. The emptiness is not surprising once mass and volume are considered together. Stable orbits also need separation. Planets that repeatedly pass too close exchange energy and angular momentum. Their paths can change, leading to collision or ejection. The surviving 8 planets occupy an arrangement that has persisted for billions of years, with average distances large compared with the sizes of the worlds. If you placed Earth and Venus only a few planetary diameters apart on independent solar orbits, their repeated gravitational interactions would prevent the tidy architecture we know. Instead, even at their closest, tens of millions of kilometers separate them. The gap protects continuity. Moons demonstrate the same principle locally. Each planet has a region where its gravity can retain satellites against the sun's pull, often described through the Hill sphere. Regular moons occupy a fraction of that region. More distant or highly tilted satellites can be less stable, especially when other moons in the sun perturb their paths. Resonance can create either order or absence. Pluto's 3-2 resonance with Neptune preserves their separation. Jupiter's resonances help carve gaps in the asteroid belt. Mimas helps structure the Cassini division. Galatea helps confine Neptune's ring arcs. Empty-looking bands can be the visible signature of repeated gravity. Collisions continue, but they are rare on human timescales because objects are small relative to the available space. Over 4.6 billion years, rare events still matter. Impacts build craters, break asteroid families, release dust, and change rotations. Long time compensates for low density. The current system is therefore not an untouched void. It is the result of removal, concentration, scattering, capture, and survival. Every planet represents material gathered into one place. Every broad gap represents countless paths that did not remain filled. Emptiness permits the planets to keep their identities. Earth is not continually brushing against Venus. Jupiter does not graze Saturn. Neptune can complete a 165-year orbit without meeting another planet along the way. The room is part of the mechanism. Without the intervals, there would be no enduring arrangement to map. Watching the young system evolve, you would see matter gather as broad regions cleared. We have talked about a sun 1.4 million kilometers wide, holding nearly all the mass, and an Earth only 12,756 kilometers wide, waiting 1 astronomical unit away. We have talked about Mercury at 0.39 astronomical units, Venus at 0.72, Earth at 1, and Mars at 1.52. 4 rocky worlds occupy the bright inner region, yet even their smallest orbital gaps are measured in tens of millions of kilometers. We have talked about the Earth and Moon as a local pair separated by 384,400 kilometers, a distance that feels immense until the complete pair shrinks to 1 point on a solar system map. We have talked about solar wind, magnetic fields, photons, dust, and radio waves. The apparent nothing between worlds has particle weather and invisible structure. Empty never required absolute absence. We have talked about the asteroid belt, where mile-scale bodies may be separated by millions of kilometers, and the combined mass of all asteroids remains below the mass of the Moon. The crowded wall belongs to illustration, not navigation. We have talked about Ceres and Vesta, distinct small worlds whose labels appear close on a chart, while a spacecraft needed years to travel from one to the other. We have talked about Jupiter at 5.2 astronomical units and Saturn at 9.58, each surrounded by a compact archipelago of moons inside a vastly larger orbital territory. We have talked about Saturn's rings, 282,000 kilometers across, and often only about 10 meters thick, a broad structure made visible by enlarging what would otherwise disappear edge on. We have talked about Uranus at 19.2 astronomical units and Neptune at 30.05. The gap between them is larger than Saturn's full distance from the Sun, and Voyager 2 spent more than 3.5 years making that single crossing. We have talked about the Kuiper Belt from roughly 30 to 50 AU, with hundreds of thousands of substantial icy bodies possible, and no expectation that a traveler would see them crowding a window. We have talked about Pluto, Charon, and Arakoth, where a 9-year spacecraft journey revealed glaciers, haze, canyons, and the gentle joining of ancient building blocks. We have talked about the solar winds slowing at the termination shock and yielding at the heliopause around 120 astronomical units in the directions sampled by the Voyagers. Interstellar plasma begins while the Sun's gravitational domain continues. We have talked about an Oort cloud never directly observed, perhaps beginning at 2,000 to 5,000 AU and perhaps reaching 100,000 AU. A spherical archive is inferred from comets that spend almost their entire histories unseen. And we have talked about Proxima Centauri at roughly 265,000 astronomical units, the next star beyond a solar domain, so large that its outer estimate already reaches a meaningful fraction of the interstellar gap. The sequence does not become crowded as it expands. It becomes more sparse, more uncertain, and more dependent on gravity revealed through motion. The honest answer is yes. The solar system is emptier than the familiar pictures imply. The planets are not close neighbors in a row. They are minute concentrations of matter traveling along paths whose intervals dominate the dimensions of the system. The answer needs its second half. The solar system is not an inert vacuum containing 8 isolated balls. Sunlight crosses it. Plasma flows through it. Magnetic fields curve across it. Dust migrates through it. Gravity organizes bodies across distances that leave no visible connection. If you could occupy an arbitrary point inside a sphere reaching to Neptune, the chance of landing inside a planet, moon, asteroid, or ring particle would be vanishingly small. Most possible locations would provide no nearby solid surface, yet instruments at that point could still detect the sun, charged particles, fields, radiation, and the motion of distant bodies. Emptiness is therefore a statement about density, not significance. A cubic volume may contain almost no matter while still carrying energy and information. A long gap may contain no planet while determining communication delay, spacecraft power, orbital stability, and the timing of every mission. The asteroid belt makes the distinction visible. It contains an enormous number of objects in total and remains easy to cross without seeing a large one. The Kuiper Belt extends the same logic across a wider, colder region. The Oort Cloud takes it to an uncertain spherical extreme. The planets themselves concentrate complexity. Earth gathers oceans, atmosphere, rock, metal, and life into a sphere 12,756 kilometers across. Jupiter gathers storms, moons, radiation, and most planetary mass into one local system. Saturn gathers billions of ring particles into a plane thin enough to vanish from the side. Between concentrations lies duration. A mission spends years and cruise for hours or days near a destination. New Horizons crossed darkness for more than 9 years before its rapid Pluto encounter. Voyager 2 traveled 12 years for a sequence of 4 giant planet flybys. Our diagrams close those years into centimeters. Their purpose is to show relationships, and they do. Their cost is the felt scale. To recover that scale, the dark part must be restored. Restoring it does not make the solar system bleak. It makes every occupied place more distinct. A moon orbiting an ice giant is not one more dot in a busy display. It is a preserved world with no comparable surface for millions of kilometers. The solar system is an architecture of rare islands and long influence. It is emptier than the picture. It is fuller than nothing. Every human life has unfolded on one of the small occupied places. The greatest journeys on Earth cross only a tiny fraction of its surface. The greatest journeys beyond Earth have reached a modest selection of neighboring islands and sent machines farther. If you stood on a plane at night and removed the atmosphere from the view, most directions would not lead quickly to a world. They would pass the moon's orbit, cross planetary paths at empty locations, leave the realm of the planets, and continue through the heliosphere. Direction alone does not produce a destination. Timing matters. This is easy to forget because the sky compresses distance onto a dome. Mars, Jupiter, and Saturn appear among stars that are millions of times farther away. A bright planet can look close to a distant star. The eye records angle, not depth. Astronomy restores depth by measuring parallax, orbit, brightness, spectra, radar echoes, and signal time. Each technique turns a point of light into a location. The resulting map is not a decorated ceiling. It is a volume with layers of time. When you see Jupiter, the light is tens of minutes old. When a telescope records Pluto, the reflected sunlight has traveled outward for hours and then back inward for hours more. When Voyager sends a carrier tone, the receiving antenna listens to the condition of a machine from the previous day. The delays do not sever connection. They define its pace. Information continues to arrive because the gaps are transparent enough for light and radio. Gravity continues to organize motion because distance weakens its pull without ending it. A sparse system can remain a coherent system. Earth's smallness inside this volume is not a measure of human importance. Physical size and meaning answer different questions. A page of writing may weigh less than a blank stone while carrying more information for a reader. A thin layer of life on one planet may be rare without being large. The same scale that makes Earth tiny makes its conditions specific. This atmosphere, this magnetic field, this orbit, this moon, this long-lived sun. None fills much volume. Together they provide the only inhabited environment currently known. Farther worlds enlarge the context. Venus shows an Earth-sized planet transformed by atmosphere. Mars shows a smaller planet that lost much of its early habitability. Icy moons show that internal oceans can exist far from direct solar warmth. Pluto shows geology continuing under faint light. The dark intervals keep these experiments separate. The solar system does not blend them into one environment. Each island develops under its own combination of mass, composition, sunlight, impacts, and time. We live on one result, looking across the room between all the others. Return to the model with the 14-centimeter sun. Mercury is a grain at 5.8 meters. Venus waits at 10.8. Earth is a blue fleck at 15. Mars stands near 23. Then the walk opens. Jupiter at 78 meters, Saturn at 143, Uranus at 287, Neptune at 450. The planets have become almost invisible before the model has left the neighborhood. Continue outward, and the Heliopause lies around 1.8 kilometers away. The nearer possible beginning of the Oort Cloud waits about 30 kilometers from the small sun. Its distant outer estimate reaches roughly 1,500 kilometers. One astronomical unit is 149,597,870.7 kilometers. That was the first ruler. It remains the useful one. 1 unit to Earth. 5 to Jupiter, 30 to Neptune, about 120 to the edge of the solar wind bubble, thousands to the beginning of the distant comet reservoir, hundreds of thousands to the next star. The numbers grow, but the pattern stays calm. Matter gathers, space opens, gravity reaches across it. Light carries the news. If you could look back from beyond Neptune, the sun would be a bright point and the planets would vanish into its glare. Nothing in the view would reveal oceans on Earth, volcanoes on Io, methane rain on Titan, tilted canyons on Miranda, or nitrogen glaciers on Pluto. Detail belongs to approach. From far away, the solar system becomes one star with a faint surrounding history. From within, it becomes countless local histories divided by journeys. Both views are true. Neither fits comfortably inside the other. The emptiness is not a flaw in the design. It is the design. It gives orbits room to persist, worlds room to differ, and light room to tell one island about another. The familiar poster can now return. 8 planets beside a star. A belt of rocks. A border near the edge. It remains a useful index, but behind every small gap on the page lies a crossing measured in millions or billions of kilometers. The page is crowded. The system is not. Small worlds, long light, a quiet architecture, one star holding the dark together. Good night.